Uh, Hello students. So in this class we'll discuss the properties of DFT. Okay. So so the important properties that we are interested in here, unlike the properties of the Z transformer DTFT that we studied earlier, here a DFT by virtue of its the the method by which entire DFT has been conceptualized, there are some interesting properties that arise. Okay, so periodicity is one of them, and symmetry. Okay, and one more thing that I want you to concentrate on is this weird circular convolution property. Then all the properties that are almost similar to that of DTFT. Remember, similar, not same. Okay, then we will try to uh, you know see if there is any possibility of doing linear filtering with this DFT also. We know linear filtering is nothing but our linear convolution, and in the previous semester we had seen that using DTFT we can do linear convolution of discrete time sequences. Using a normal Fourier transform, we could do linear convolution or linear filtering of continuous time signals. Since our subject is digital signal processing, here also we'll try to see that. What was the problem, by the way, in DTFT? DTFT could do find the linear convolution of the sequences, but then the problem is the moment you convert the signal to DTFT, it would become continuous in nature. So it was not a possibility. Okay. Anyway, let us go ahead. Hmm. So which are the properties? First property is the periodicity property. What do the properties say? Uh, this is obvious. Okay, we know that DTFT was periodic, right? We know DTFT was periodic with period of 2 pi, right? We know DTFT was periodic with period of 2 pi. That means it would be symmetrical. Symmetry not necessarily. We will see that. So DTFT was periodic with period of 2 pi. That means after every 2 pi duration, the same thing would repeat. Okay, same thing would repeat, and so on. Here also, that means here, so it doesn't make any difference, right? You whether take from minus pi to pi or 0 to 2 pi. Let me consider 0 to 2 pi for my convenience here. Okay, from say from 0 to 2. Okay, so let me tell you once again, the DTFT was periodic from 0 to with period of 2 pi. After every 2 pi, the same thing would repeat. Now, since DFT is a sampled version of DTFT, since DFT is sample, that means for every duration, for every 2 pi duration, we are taking n samples, so that after every n sample, the same sequence is going to repeat. Okay, so this is, we are convinced DFT is periodic, but this is something interesting. This is something interesting. They are telling x of n is also periodic. We know DTFT, the discrete time Fourier transform, would exist for aperiodic sequences only, right? Remember, as we studied in the previous semester, the periodic sequences have Fourier series, whereas the aperiodic signals have Fourier transform. But while you are trying to derive the DFT from DTFT, we have made some compromises. And you might remember at certain point, we broke this entire thing into several segments, infinite segments, and then we changed the order of summation. And finally, we ended up getting something like this. Okay. So even during the derivation of DFT, it was told that when you take a signal x of n, say this one. Okay, let me take this x of n. You take the DFT, and then to be able to take an inverse. Okay, you take a sequence x of n, you take DFT, then you take an inverse. Then this sequence is no more our aperiodic sequence that we took for processing. Rather, it becomes something like xp of n, right? Rather, it would become something like an xp of n, which is conditionally equal to x of n only from 0 to n minus 1. Okay, right? Remember, okay, that's what we have been telling. We will end up getting some xp of n, which is the periodic version of x of n. That means it is x of n repeating after every n samples. Okay, this is one property. Let us see the proof of this property. So here you can see how the entire thing has been derived. Okay, so here we have started with an expression of DFT for a change. Okay, expression for DFT. K was replaced by K plus N as part of our requirement for the thing. And it so happened here in this particular exponential, see, the K was replaced by K plus N, so that we will get this particular term e to the power minus j into 2 pi n into n into n. So this entire term you can see for any value of small n, since there is a capital N present, it is always equal to plus 1. That is why this particular term x of k plus n, that is why x of k plus n turns out to be simply x of k. So is it true for x of n also? If at all I had to derive the IDFT expression, here x of k would be replaced by x of n, right? The expression for IDFT. Then here I would have a 1 by n. Then here instead of an n, I would have a k maybe. And 0 to n minus 1. Here I would have x of k. And then instead of a minus, I would have a plus. Remaining all the things would remain almost similar. Here I would have n replaced by n plus capital N. In that case also, I will have something similar. I would have a plus here. The 1 by n would still remain. I will have this term also. Here I would get e to the power minus 2 by n into capital N into k I would get. Okay. Now this particular k here would be automatically, this particular term, since it would automatically lead to a plus 1, I would still end up getting x of n. So the proofs are very, very similar only. Proofs are very, very similar. Okay. So second property is the linearity. I think this is a very trivial property. The addition remains a addition. Okay, constants remain the constant. That means the superposition theorem is satisfied for DFT also. Okay, it was there for DTFT, it was there for that transform. It is satisfied here also. Okay. So let us analyze more on this periodicity property. What is this periodicity property? So actually you can see here, our x of n, whatever it claim, when you take the DFT and take IDFT, it turns out to be an xp of n. Okay, now this xp of n will be x of n from a period from 0 to n only. Okay, the signal is periodic and this xp of n is equal to, conditionally equal to x of n from 0 to n minus 1. Above that it is going to be a periodic signal only. Okay, above that it's going to be a periodic signal only. Remember that. Remember that. So what will happen now? Suppose I have a sequence of length 4, but I intend to take a 5-point DFT. Say I have a sequence of length n is equal to 4. Suppose I have a sequence of length n is equal to 4. Say my sequence is 1, 2, 3, 4. Okay. Then say I decide to take a 4-point DFT. My x of n. So this 1, 2, 3, 4 will be my x of n. Okay. When I take a 4-point DFT, take IDFT, the x of n will convert into xp of n. So I get 1, 2, 3, 4, 1, 2, 3, 4. The same pattern would keep repeating. After every 4 samples. Same pattern would keep repeating after every 4 samples. Fine. Okay. But what's going to happen? If at all I take n is equal to say 5? What will happen if n is equal to say 5? Then what's going to happen? You have your original sequence, whatever it is. Say here in this example, whichever I have taken, the numbers assumed are 1, 3, 4, 5. Okay. Here number assumed are 1, 3, 4, 5. So what's going to happen? I have my 1, 3, 4, 5 intact. Okay, which is the length of sequence. But since I decided to take my value of n is equal to 5, which is 1 greater than actual length of the sequence, I have to stuff in a 0. Okay, a 0 has stuffed in. Okay, so we have seen earlier with DFT, higher value of n is not going to hurt because we will get more number of samples in the frequency domain. Okay, suppose I have sequence x of n equal to 1, 3, 4, 5 with containing only 4 samples. If at all I decide to take a 10-point DFT, then I have to stuff in 6 zeros. Okay, so after that the same pattern is going to repeat. That's the assumption. Okay, But the catch is, what if I take value of n less than the actual length of the sequence? See here, length of the sequence is 4, but I have taken a 3-point DFT. Then what's going to happen is, only 3 points are in consideration. The 4th point is not at all taken into consideration. It's not at all taken into consideration. That's a consequence of this periodicity. Okay, the signal can be of length 8 or signal can be of length 20. If at all you take length of DFT length more than the actual sequence length, zeros will be stuffed in. If at all you take the length of the DFT same as the length of the actual time domain sequence, then the signal will remain intact at least from 0 to n minus 1. If at all you tend to take a value of n less than the actual length of the sequence, time domain sequence, then what's going to happen? The losses will occur. The impact of 5 on the spectrum is never been considered at all. Okay, that is the consequence of the thing. Okay, so I hope you might have got the periodicity property. And one more impact of this periodicity property is its impact on the shifts that we are going to experience. Okay, so what's going to happen is, the shifts are now called as, they are not, because see, you took a sequence x of n, then the sequence turns out to be, shall be considered as a periodic sequence. Okay, the sequence shall be considered now as a periodic sequence. So period is equal to n, so that when you do the shift, okay, say I have this x of n and say n is equal to 4, then the same sequence keeps repeating after every 4 samples. Fine. Now if at all I want to take x of n minus 2, okay, x of n minus 2, the typical x of n minus 2, what does it contain? Say my sequence I have 1 2 3 4, then x of n minus 2 contain 1 2 3 4. Then what's going to happen is, actually one was there at the origin, but now at origin you will have 0, and at 1 also you have 0. The entire thing has been moved to the right by 2 locations, and zeros have been come to the left side. Because where were these zeros? These zeros were there on the left side, right? Because there was nothing on the left side. Okay, but here what's going to happen is, now we are talking about a periodic sequence being moved. Now we are talking about a periodic sequence being moved. So what happens is, the values from the left side are not zeros anymore. You can see, if at all earlier, if at all I simply move to the 2 locations to the right, zeros would be stuffed in here. Here you would get zeros. But now what's going to happen is, the value at here, these values are going to come in here. They are not zeros. They are not zeros. So that's why you can see here they have given, author has given a very nice example. The value at 0 will now go to 2. The value at 1 will now go to 3, right? The value at 0 came to 2, fine. The value at 1 will now go to 3, fine. But what's coming at 1? What is coming at 1? So the value at minus 1 is now coming to 1. Value at minus 2 is now going to 0. Okay, so they are these values. So that's why when you say shift, it's not actually a shift, but rather it is a rotate. Okay, the name used is the circular shift, and it is usually represented by x of n minus k, whatever the factor, x of n minus k, whatever the factor, and represented by, for what value of n you are considering, for what value of n you are considering. Okay, so author says that it's like keeping the values around the circle. You can see, say x of 0 is here, 1 is here, 2 is here, and 3 is here. So if at all I want to take x of n minus 1, say I want to take x of n minus 1, a circular shift, then what's going to happen? Value at 0 will go to 1. That means 1 will come here for a change. Value at 1 will go to 2. 2 will go to 3. 3 will go to 1. That means 1 which was earlier here now have come. 2 which was earlier here will now come here. 3 will now go to here. 4 will now come here. Okay, got this particular thing. This is similar to your rotate instructions in your microcontroller. Maybe did you have rotate instructions in microcontroller? Microprocessors you had, right? Something similar. Okay, something similar is what you have here. So you can see here, moving by 2 locations, x of n minus 2, you can see 1 which was here now has been moved to 2 locations to the right around the circle. value at 2 has come here, value at 3 has come to this location, and this one 4 has come here. Okay, got this particular thing, got this particular thing. Hence the circular shift. Okay, hence the circular shift. Okay, so now what's going to happen if at all my value of n is equal to say 5? So sometimes this is x of n minus 2. See, I have taken an example here. My original sequence is 1, 3, 4 and 5. Okay, my original sequence is 1, 3, 4, 5 here for a change. And say I move it to the right by 2 locations, 0 should be stuff. If I do the circular shifting, then 1 will come here, 3 will come here, 4 and 5 from the periodic extension have now occupied this place. So this is rotate, fine. Okay. What if I want to find x of n minus 2? What if I want to find x of n minus 2, but the circular shift only, but n is equal to 5, but say my n is equal to 5, then what's going to happen? Then what I have is 1 is moved here, fine, 3 is moved here, 4 came here, but then you can see since n was 5, I have considered padded in with the additional 0 to make the length 5, then I will move. So this 0, the padded value, is not going to come at this point, and this 5 is now going to occupy this location. Got this particular thing? Got this particular thing? Okay. Yes. Let us continue. I hope you might have realized what is the consequence of the whole periodic thing. What is the consequence of whole periodic thing? Okay. Now, some of the symmetry properties. Let us try to understand some of the symmetry properties. You have seen one of the properties in all the numericals that we had solved in the previous class. What was the symmetry property? You might remember, what was it? The second and the fourth values were complex conjugates, right? You have done a 4-point DFT problem and you have done 8-point DFT problem, right? So in the 8-point DFT problem, you might have seen the first value and the seventh value, they were complex conjugate. The second and the sixth, the third and the fifth, they were complex conjugates, right? That means the spectrum is same, magnitude is same, phase angle is sign change. If it is plus 45, it will become minus 45. If it is plus 90, it will become minus 90, and so on. It is just an example. Let us say so many symmetry properties are there. Okay, well, what is the advantage of having these symmetry properties? Advantage is now suppose I have to find an 8-point DFT. Okay, say I have to find an 8-point DFT, the problem which you solved in your second class, right, which was given as an homework. So what did you do, by the way? How did you do it? You had to calculate. Your friend only complained, one of your friends told that it was a lengthy problem. I had to compute how many equations you have to compute. You have to compute x of 0, x of 1, x of 2, x of 3. You had to compute 8 expressions, right? You have to compute 8 expressions. Okay, now the symmetry property says that values in the second half, if at all the sequence is purely real. Okay, I'm just quoting one example. You have seen the you have solved enough numericals and you might have understood only if the input sequence is purely real, then only the second and fourth values are conjugates, otherwise they are not, right? You might have seen it. Okay, so suppose I happen to have, say you have been asked to calculate a 64-point DFT. Say you have been asked to calculate not 8 but 64-point DFT. Then the same property implies that now you don't have to go and calculate 64 equations, but you may need to calculate, except for the first value and the midpoint, except for what you need to calculate now only 64 divided by 2 plus 1. That is how many? 33. Now you need to calculate only 33 equations. Isn't it cool? You need not calculate all the equations, but now you can manage it only half the equations, because we know that the input sequence is purely real and the remaining values shall be calculated just by simply changing the sign of the imaginary part. Okay, so all these properties of DFT or any transform for that matter are actually are actually used to reduce the computational complexity. Okay, before going to the properties, let us have clear breakup of this entire expression for DFT or IDFT in terms of the real and imaginary component. Author here has tried to do that. So author, what it does, it say I have a sequence x of n is equal to a plus jb. Then a is the real part and b is the imaginary part, right? Say I have a plus j into b, then a is the real part of x of n and b is the imaginary part. And say I get the DFT of this particular sequence, say I get the DFT of this particular sequence, then what I will say, my first term is 2 minus 2j. 2 is the real part, 2j is the j2 is the imaginary part. Okay. Are you getting this particular thing? Let me take you to a numerical. If at all I have an example, let me check. Okay. So here, suppose I have sequence x of n. The real part of the sequence is the xr of n. Xr of n would be, what will be the real part of the sequence? It's going to be 1, 2, 0 and 1, and its imaginary part and its imaginary part would be what it would be, 2j, 2j, j and j. No, I'm telling it the wrong way. Okay, imaginary part is accompanied by a j, but the value is, imaginary part is 2, 2, 1 and a 1. Got this particular thing? The real part is 1, 2, 0 and 1. Okay, same is the case for its DFT also. Okay, so XR of n, XFN, they are vectors actually. They are not a single value. Okay, it's a array, I would say. Okay, not vector, it's a array. Okay, now let us go back. What ease does it give us? What ease does it give us? Let us check. So here, what author says is, author has just, this is not a proof of anything. It's just a statement where he has broken down the things. Okay, so you can see, if at all this is x of n to be broken down into a real segment and the imaginary ones and the corresponding DFT, author says that, okay, what is the component, by the way? What is the DFT? X of k e to the power minus j. What is the DFT expression? What is the expression for DFT? Let us see if at all I have the expression for DFT here. Wait a second. Yeah. Here is the expression for my DFT. Here is the expression for my DFT. You can see x of n can be real, can be imaginary, or it can be complex. But it can be broken down into some a plus jb. X of n can be some a plus jb term. Okay, and this particular twiddle factor is also complex. It can also be broken into cos theta minus j sin theta, minus or a plus something. Okay, cos theta minus j sin theta thing, right? This can also be broken into two parts. Okay, now if at all I multiply these, what do I get? Real multiplied by real, real multiplied by imaginary, imaginary multiplied by real, imaginary multiplied by imaginary. So j and j square is minus 1, something like that. Okay, so finally once you get an answer, your answer is also going to contain a real part and the imaginary part. Okay, real part and imaginary part. So when this entire thing is viewed from a programmer's point of view, okay, so because you might have seen in your microcontroller and all, there is no a plus jb multiplied by c plus jd, you cannot do. A plus jb plus c plus jd, you cannot do. You have to separate them, the real and imaginary. Okay, so this is from a implementation point of view. Okay, be curious and see how it actually reduces the computational burden. Okay, now you can see here the real part of the answer, if at all you calculate and represent e to the power j 2 pi by n into kn as cos minus j sine, then you can see the real part of the answer can be broken into this particular expression. Imaginary part can be broken into this particular expression. Okay, if at all you want to calculate DFT on HDL, okay, you are very logged, whatever you are learning, then you have to use these expressions only with a lookup table for this. HDL cannot compute these values. You have to have a lookup table there. Okay. Similarly, the case for IDFT also. Similarly, is the case for your IDFT also. It can also be broken into two expressions. Okay. This is an initial preparation. Now let us see what do they do from these. Okay. What properties are we talking about? So the property first that is coming into picture is what if x of n is real? Okay. If the sequence x of n is real, what's going to happen? If the sequence x of k is purely real, then author says that if the sequence is real, then author says that here. If the sequence is real, author says that x of n minus k is equal to x conjugate of k. So n minus k is equal to x conjugate of k. Okay, we have seen enough examples of these. Okay, just keep a check. So what's going to happen, by the way, if x of n is real? What does it actually mean? Okay, let us go back and see here. Let's go back and see here. If sequence x of n is purely real, then there will not be this computation at all. What this particular thing? If sequence x of n is purely real, then my DFT computation here will not contain this particular expression at all. That means those many number of multiplications have been reduced because imaginary part of your input is 0. Okay, and you also do not have this particular expression at all. Okay, got the thing. Those two expressions will not be there at all. So your expression of the DFT is going to contain this term plus j into this particular term, which is xr cos 2 pi by n into kn minus xj into xr sin 2 pi by n into kn. That's what it is going to contain. Okay, that is one of the way in which author wants us to see. Okay, so that which property can save us how many number of computations. Okay, so here this is one implication of the thing. There is a proof of this particular property. It is there in the textbook. Now to keep things simple and interesting, I am omitting all the proofs of the properties. They go as a homework. We will rather concentrate on its impact on the computations and the ease with which those properties let us do filtering aspects. Okay. So as you can see, having the sequence which is purely real is reducing us so much of the burden. And I was telling earlier, a 64-point DFT computation of a sequence which is purely real is letting us calculate only we can manage with only computation of 33 expressions, half the expressions, almost half, right? If at all we're talking about 1024 DFT, which is a regular thing in your 5G transmission, then half the computations themselves are reduced because you can predict the remaining half, what the value is going to be. And again, these parts are going to be removed. Similarly, if at all I say if the sequence x of n is purely imaginary, then what's going to happen? If at all my sequence x of n is purely imaginary, then this computation will not be there at all. Okay, and the same symmetry property is still going to be hold good. Only thing is now j is the constant. Now j is the constant that is getting multiplied, and your linearity property can be applied. Okay, be curious and think about the statement which I made just now. Okay, so now let us talk. Okay, so now you've got this particular property. We have seen this particular thing. Okay, second thing is, what if the sequence is real? What if x of n is real and also even? Okay, what is meant by even, by the way? We know real. What is meant by an even sequence? Even sequence is, okay, let us talk what is a even sequence. Let us say I happen to have a sequence. Tell me this particular sequence here. What is this particular sequence? Say I have 1. Now see this particular sequence. Let me draw a sequence here. There. Okay. Sequence here. Okay. See this particular sequence. Say this value is 2, this value is 1, and this value is say minus 2. Okay. Then if at all I take x of minus n, what do I get? Say this is 0, this is 1, this is 2, this is minus 1, and this is minus 2. Okay, if at all I do x of find x of minus n, what is x of minus n? All the values at minus 2 will go to plus 2, all the values at plus 2 will go to minus 2, and so on. You can see this particular sequence. If at all take the sequence, and if at all I simply take a minus of it, right, reflection, then the things are same, right? You remember this property we discussed in signals and symmetry. It's a symmetry property, okay, of the, if the signal is symmetric across the y-axis, the values on the left and values of the right are same. Unfortunately, okay, the x of, if x of minus n is equal to x of n, we would call the sequence as even. If x of minus n is equal to x of minus n is equal to minus of x of n, we would call the sequence as odd. Remember this. Remember this. If x of minus is equal to minus of x of n, we would call the sequence as odd, right? Odd even we studied in the previous semester. Okay. Now here for a change, now we are in DFT. Once you talk DFT, there are no values on the negative side. DFT always starts from 0 for the matter. Okay, DFT starts from 0. So now the whole definition of an even sequence completely changes. Now it is not a regular even sequence. We call it as a circularly even sequence. Remember, a circular. What is meant by circularly even sequence? Let me draw a circle. Let me draw it now. Okay, this is my origin. Okay, this is my origin. Say there are 4 values. Say there are 4 values. Usual method is the anti-clockwise method. Usual method is anti-clockwise. Okay. Say I have a sequence here. Say the sequence is 1, 6, 3, 6. Say I have a sequence 1, 6, 3, 6. Okay. If at all, okay, and this is my origin. Okay, this is my origin. This is 0th value. This is first value. This is second value, and this one is third value. Okay. 0th, first, second, and third value. Say now I trace it from the clockwise direction. Okay, what I did, I was traced by anti-clockwise direction. Okay, this is usual. 0, 1, 2, 3. So the sequence is 1, 6, 3, 6. Okay, that's the sequence. If at all I trace it now from origin in the clockwise direction, what do I get? I still get 1, right? 1, 6, 3, 6. It's still the same, right? You do it from the left or you do it from the right, the sequence still remains the same. Then I call this particular sequence as a even sequence. Okay, then I call this sequence as an even sequence. Okay. So let's take one more example. Now, say I have a sequence x of n is equal to, say I have a sequence x of n equal to 1, 2, 3, 4. Okay, say I have a sequence x of n equal to, then x of minus n, while I write a minus here, let me put one more bracket and let me write a 4. Now what will be this x of minus n? What will be this x of minus n? To find this x of minus n, what I have to do is, first I have to draw a circle. Then afterwards I should mark the values. 1, 2, 3, 4 in the anti-clockwise direction. This is usual. When I want to find the x of minus n, the reflection, since I am talking circular nature of the sequence here, I have to now start from origin, go to the clockwise direction instead. Okay, then first value is 1 because value at origin will remain same. Second value what I get is 4, then I get a 3, and then I get a 2. So 1, 4, 3, 2. 1, 4, 3, 2 is my x of minus n. Okay, got this particular thing. This is how we find it. Now, if at all you can see, is this particular sequence even? Is this sequence circularly even? No, right? Because if you get x of n, it is 1, 2, 3, 4. If you get x of minus n, it is 1, 4, 3, 2. Okay, so it's not circularly even. Whereas if at all I talk about a sequence x of n is equal to, say, what's the number? Say I have 1, 6, 3, 6. Say I now talk about sequence 1636. Then for this particular sequence which I had drawn earlier, you can see the x of minus n also remains. X of minus 1 also remains. Let me draw it here if at all you are getting confused. Let me take the eraser. Okay. The value. So what is the sequence once again? The sequence is 1 6 3 6. This is the origin. Even if you go from the right side, even if you go in the anti-clockwise, it is 1636. Even if you go from the clockwise direction, it is 1636. Okay. So this particular sequence is a even sequence, a circularly even sequence. Okay. So why are discussing this? Because here we got this particular thing. Similarly, let us talk circularly odd sequence also. What is a circularly odd sequence? We know odd, right? X of min is equal to minus x of n was odd sequence, right? A typical odd sequence was x of minus n. If at all it was equal to minus of x of n, x of minus equal to minus of x of n, then the sequence was called odd. Okay. What such sequences would be? We remember that cos sequence, cos wave, right? You remember cos wave is a even wave, whereas a sine wave you can see is a odd one, because values on the right side and the values on the left side, they change their sign. Anti-symmetric is what we call it. So now if at all we're talking about circular symmetry, say let me give an example. Say I have x of n is equal to what number should I take? Say x of n is equal to, say x of n is equal to say x of n is equal to 1, not 1. Let me take a 0 here. Okay, let me take a 0 here. 0 minus 1, 2 and plus 1. 0 minus 1, 2 and plus 1. Okay. Now shall I try to do this particular thing? Now let me draw this. Now let me draw this on the circle. Wait a second. Let me take you to the whiteboard. Whiteboards are cool. Let me take you to the whiteboard. Okay. And here. Okay. Say I have a sequence x of n is equal to, say here I have a sequence x of n equal to 1 minus 2 0 2. Okay. So now let us try to draw this around the circle. Now I will draw the circle once again. God, it's not looking like a circle anyway. Now if at all I draw this thing, so what is it? 1 minus 2 0 and 2. Okay, so what is the rule? If at all you trace from the anti-clockwise direction and you trace from the clockwise direction, the values, the magnitude should remain same, the sign should change. Okay, now shall I try from the right side? What do I get? If at all I trace from the right side, it is 1 minus 2 0 and plus 2. Okay, now if at all I take from the left side, okay, what is the theorem? The equation says that if at all the sequence is purely odd, x of minus n should be equal to minus of x of n. Okay. Now x of minus n means what? Okay. Now what is x of minus n? Say this is x of n. Okay. Minus of x of n. X of n multiplied by minus 1. What is that? X of my n multiplied by minus 1 is minus 1, 2, 0 and minus 2. Minus 2. Now if it all simply trace from anti-clockwise direction, then what do I get? Then what do I get? X of minus n. That would be my x of minus n. That would be my x of minus n. How would that look like? That would be 1, 2, 0, minus 2. Okay, now we can see this expression and this expression, are they same? These two expressions, are they same? These two expressions, are they same? these two, hmm? 2 and 2 matching, 0 and 0 matching, -2 and -2 matching, but the value at origin, oh, they are not matching. Okay, so what would be a better sequence? If at all I have my x of n is equal to 0, then problem is solved. If at all I have x of n is equal to 0, minus of 0 is also 0 only. So an example of a nice odd sequence, an odd sequence, remember, always will have the value at origin as 0. For example, if at all I have 0, -2, 0 and 2. Now you can see. Try the entire exercise with this. So if at all you come from the right side, change the sign, come from the left side. It's still going to be same. Sorry, not right. Anti-clockwise and change of sign and clockwise. So this here is an example of a circularly odd sequence. Okay. Now what I will do is, today I will share very small exercises on the shifts. Okay. Be comfortable with them. Tomorrow, okay, in the next class, you have to submit the assignment the very day when the assignments are given. Okay. In the next class, we'll continue from where we have stopped, right? Where did we stop, by the way? We stopped here at the properties of DFT, right? Very interesting topic. Okay, so knowing the properties of DFT lets you manage, implement the circuits on your HDL or a microcontroller or a microprocessor with less number of multiplications, less number of additions. What we call them as low power, energy efficient devices. Okay, so okay, let me end this thing here.